Good day, everyone, and once again we are back together. All right, so I am going to be looking at some revision for paper two. All right, if you haven't subscribed, please just make sure you're part of the family. All right, so we're going to look at this Gauteng exam. All right, it was a prelim exam, so let's get right into it. We've given hydrogen gas that is prepared by the reaction of methane and steam as shown in the reaction. Okay, so they say methane and steam are sealed in a 2 cubic decimeter container to react and are allowed to reach equilibrium at temperature T. Right, so first of all, they say state Le Chatelier's principle, right? You know, in a closed system, one of the factors that affect equilibrium changes, the equilibrium will oppose the change, and a new equilibrium will be established. All right. Of course, there are many ways in which you can state that are different from mine. You're welcome to use those. Right. So they say use Le Chatelier's principle to explain how the following changes will affect the yield of H2. So remember, our focus here is to look at the yield of H2, right? Now, they say how will adding a more CH4. Now, please remember, so when you're stating Le Chatelier's principle, right, or using Le Chatelier's principle, so first always state the change that occurs and what the result will be, right? So 6.2.1, I am going to say, right, an increase in CH4, okay, an increase in CH4 will increase, or rather will favor, okay, so it will favor the reaction that uses up CH4. That uses up CH4, right? So which reaction is that? That's the forward reaction. The moment I increase CH4, it means that I am going to favor the reaction that is going to use CH4. Why? Because now we have to get rid of the excess amount of CH4 that's been introduced, right? So the forward reaction uses CH4, and so the forward reaction is favored. Okay, is favored. So as a result, what are we going to encounter? We're going to encounter an increase in the yield of hydrogen, right? Now, actually, of course, these are the type of questions wherein they would ask me, will it increase, decrease, or remain the same? And I probably would have answered the question first and say, well, my yield would increase in this case, right? And of course, just have the explanation afterwards, right? Right, let's go to 6.2.2. Okay, so they ask us a decrease in the volume of the container. Now remember, anytime they ask us about volume or concentration, what we're going to do is check the number of moles of gas on the left and on the right hand side. Now note, so on the left hand side, how many moles of gases do we have? We've got 1 and 1 there. So we've got a total of 2 moles of gases, right? And on the right hand side, we've got 1 and 3. So we've got 4 moles of gases there. Now I want you to please note, whenever I decrease volume, so that means I'm increasing the pressure, right? So when I decrease the volume, right, what I will do is I will favor the side that has less moles of gas, right? Note it is gas moles, not just anything else, right? So I will favor the side that occupies less volume. So that's where we've got less moles of gas. Where do we have less moles? On the left-hand side. So which means my equilibrium will move to the left, right? Will shift to the left. So as a result, what will happen to the yield? My yield should decrease, right? So let's write that down. So firstly, we know that our yield should decrease, okay? And firstly, we're going to say, well, a decrease in pressure, or rather a decrease in volume, right, will favor the side that occupies less volume, right? Or rather, that occupies less volume. Okay. So the left-hand side rather, or the reactants occupy less volume. Okay, and so less volume. So the reverse reaction is favored. The reverse, I should say. Okay, so the reverse reaction is favored, right? And actually the yield will decrease. Okay, right, so in this case, every time the change, okay, and the reaction that is favored, why it's favored, and in this case, we're going to look at the result. All right, now let's go to the next question. Now, they say the sketch below shows the changes, right? So they give us that sketch there. The changes of methane and steam and carbon monoxide as the reaction proceeds for the preparation of hydrogen gas in a 2 cubic decimeter container. Right, now first they said write down the reason why there is no change in the number of moles in or of each of the gases between T1 and T2. So you note in that case what what has happened is that we've reached equilibrium, right? I'm not going to write that down. So 6.3, just remember that equilibrium is reached. Okay, right. So the next question. Okay, right. So just remember that we've reached equilibrium. And then they say use the information on the graph to calculate the equilibrium constant for this reaction at T. Now, guys, I want you to note, it is possible for us to get information in graph form. And what does this information tell us? Right, you see you've got CH4 there, right? It says you started with 1.2, and 1.4 rather, and for steam you started with 1.2. So meaning for both CO and hydrogen, you started with nothing. Both of them start at 0. Right, so let's do this. Let's fill in our table, right? And I know you guys already know a lot about the rice table, right? Okay, so, right, I know that most of you like the ratios first. Okay, so I usually don't fill in the ratios. I actually put them as part of my reactions there, right? So we had CH4, we had steam, okay, we have CO, and we've got H2. but remember H2, there's 3 of that there. Right, so please remember we've got initial, that's in moles. We've got change in moles. We've got equilibrium, that's moles, and as well as equilibrium concentration, right? And this is in moles per cubic decimeters. Okay, right, so what did we start with? We said we started with 1.4 of CH4 as well as 1.2 of steam, right? But for each of these, we started with nothing, right? And then at equilibrium, we're actually given one of the values, and that's for carbon monoxide. So we've got 0.6 over there of carbon monoxide at equilibrium, right? So in this case, we're going to say, right, at the end, we've got 1.6 moles of carbon monoxide. So there we go there. Now remember, guys, that the ratio we're going to use in the change moles, right? And what I'll do is that I'll write that in a different color. Okay, so all we simply do, take the one that has the most information. I started with nothing, that's CO, right? I started with nothing. At the end, I've got 1.6. How much did I produce? I must have produced 1.6, right? I mean 0.6. Why did I say 1.6? Sorry about that. So that would be 0.6, okay, right? So that's the amount that we got at the end there. That's 0.6, right? So I started with nothing. At the end, I've got 0.6. I must have produced 0.6. Okay, apologies about that. Right, so then I use my ratios. Now, guys, note, I'm going to make this as quickly as possible, right? For every 1 mole of carbon monoxide, I get 1 mole of steam, right? H2O. So for 0.6, I should get the same amount. So that will be 0.6. The same thing is true for CH4. For 1, there is 1, right? So in this case, this will also be 0.6. And look at this. For 1 mole of CO, I get 3H2. So that means the amount should be 3 times there. So 0.6 times 3 will give me 1.8, right? Okay, so let's quickly have a look at what we have left. Okay, so we started with 1.4 of CH4. We use 0.6, and what do we have at the end? We've got 0.8 moles, right? We started with 1.2, used 0.6, and what do we have at the end? We've got 0.6. And of course, we started with nothing, produced 0.6, we've got 0.6 at the end, right? And we started with nothing, produced 1.8, we should have 1.8 at the end. And remember, our volume was given to us as 2 cubic decimeters, right? There it is given there. Okay, so we know that we're going to use our volume. Now remember, concentration is number of moles over volume. So we're going to say, right, 0.8, okay, divided by 2, and that will give us 0.4. Okay, and that gives us 0.3. That gives us 0.3, and 1.8 divided by 2 gives us 0.9. Okay, so those are your values, right? And of course, now we can calculate Kc, right? Molar concentration of the products. What are my products? It's CO and H2 and H2, but the coefficient of H2 is 3, so that becomes the power. Okay, so this is divided by CH4. Now, please remember that you only For KC calculation, you only use guesses. So in this case, all of them are guesses. So that's why I'm using them, right? So products over reactants. And now I'm going to substitute for each and every one of them. So we've got 0.3 and 0.9 cubed divided by, okay, CH4, we got 0.4 and 0.3 of that. Okay, just to make our calculation easier, those are the same. We can cancel them out. And what do we get for our Kc value? So that's 0.9 cubed. All right, and this is divided by 0.4. Okay, so I get a value of 1.8. Okay, 1.82. That's our Kc value. And in this case, it tells us our Kc value is greater than 1. So it does mean that the concentration of the products is greater than that of the reactants, right? Okay, finally, they say to us the temperature T is increased. How will this affect the Kc value for the above reaction? Will it increase, decrease, or remain the same? Now, please remember, guys, so delta H in this case is positive, so it's greater than 0, right? So that means that the forward reaction is endothermic, right? So this is plus heat on the left-hand side. Okay, now, because you've got heat on the left-hand side, or in this case, you've got an endothermic reaction, every time you increase temperature, you favor the endothermic reaction. So that means the forward reaction will be favored if we increase temperature, right? Just like actually they said decreased, sorry. So the temperature is decreased, so we're going to favor, in this case, the reverse reaction, the exothermic reaction, right? So the reverse reaction will be favored, and as a result, that means that our Kc value should actually decrease, right? So that's 6 point, I think that was 6.4, right? 6.5 actually. 6.5, our Kc value should actually decrease. Remember, anytime you are favoring the reverse reaction, your Kc value should decrease. Okay. All right. In fact, we should just write decreases. Okay. All right. So that is how the cookie crumbles. I hope that you enjoyed this question, right, on interpretation of graphs. Otherwise, from me for now, I'll see you guys next time. All right. Sharp, sharp.